Everybody, so the demand for sustainable and renewable energy resources has certainly intensified in recent years, probably due to the increasing global concern about climate change and the depletion of traditional fossil fuels. Now, among those various renewable energy options, wind power stands out as promising and eco-friendly as a solution, with the whole area probably being dominated by the traditional horizontal axis wind turbine. But these turbines, well, they're not without their problems. They're prone to lightning strikes, and of course, I consider them probably are quite lethal to the local wildlife. If they're not built properly, they have a terrible propensity to fall down because they only really work if you stick them up there in the air. If they overrun, that is, get too fast, the consequences can be catastrophic. And every now and then, they have a terrible habit of bursting into flames for one reason and another. So although traditional horizontal axis wind turbines have dominated the wind energy landscape, there is a growing interest in vertical axis wind turbines as an alternative and potentially a more efficient option. Unlike their horizontal counterparts, VAWTs have a unique design in which the rotor is perpendicular to the ground. The vertical orientation allows the turbine to capture wind from any direction, eliminating the need for complex yaw mechanisms used in HAWTs to align with the wind. There are several designs of VAWTs, the most common designs being types of Diraeus, Savonius and helical designs. The Diraeus design, which is characterized by a curved blade arranged in a helical shape, is particularly popular for its efficiency and its aesthetic appeal. The major advantages of VAWTs are omnidirectional wind capture, simplicity and durability, low noise levels and scalability. And the disadvantages, or if you like, the challenges and considerations? Well, the first one would be startup torque and cut-in speed. VAWTs typically have a higher cut-in speeds and require a minimum wind speed to start generating power, and that can be a limitation in areas with lower than average wind speeds. The second one is efficiency at low wind speeds. While VAWTs are brilliant at capturing wind from various directions, their efficiency at low wind speed is generally lower when compared to HAWTs. And the final one are the aesthetics and the public perception. Because although the unique designs of VAWTs can be appealing, some folks find them less appealing than the conventional HAWT with the familiar three-blade design. Public perception and aesthetics can seriously impact on the widespread acceptance of new technology like VAWTs. But generally, VAWTs are a promising avenue for harnessing wind energy with distinct advantages. However, more work is required. In the quest for more efficient and sustainable energy solutions, researchers and engineers are increasingly turning to nature for inspiration. Biomimicry is the practice of imitating biological systems and processes to solve human problems, and that's led to innovative designs across a whole range of industries, the notable example being the integration of whale tubercles into wind turbine design. Whale tubercles are small rounded protrusions found on the leading edge of humpback whale flippers. And these tubercles are not merely pretty, they serve a critical purpose in optimizing the whale's hydrodynamic performance. Researchers revealed that these bumps alter the flow of water over the flipper, reducing drag and increasing lift. And this, of course, makes it a natural adaptation. And that's captured the imaginations of science and engineers seeking to enhance the efficiency of man-made structures, particularly wind turbines. So in order to look at all of that in a practical way, what I've done is I've created this. This is the blade for a VAWT that we're going to put together. That one is without tubercles and that one is with tubercles. Now it's a very simple design, it's just 3 blades, and you'll find this in Thingiverse. The link is in the description below if you want the files. But there are 3 blades without tubercles, and we're going to arrange them into a VAWT, and to do that we've got got these two tops and bottoms, and they've got holes in them at 120 degrees and a central hole, and then you should have 8 of these and 1 of these. 6 of these just get jammed into those holes. You can glue them in with cyanoacrylic glue, and we do that with the top and the bottom, and then once we've done that, we stick those into the blades, making sure that the leading edge is all the same direction. When you've done that, that's what you'll get. Now you'll have 2 more at the same length. One goes in from the top, one goes in from the bottom, leaving a little bit stuck out. Then you'll have 2 of these, they go onto there, and we do exactly the same with that one. When you've got that far, you'll find a shorter one. These are 100 millimeters long, this is 75 millimeters long, and it goes directly in the middle like that. And of course what we need is a couple of couplers. So you slide a coupler on there, and then another coupler on that side. Then you pop that in between, put a bit of glue on there and slide it up so the coupler is halfway between the two, and you do that both sides and that will hold it together. When you've done that, grab yourself a couple of 8mm washers and put one on each side. And then a bearing on each side. These are skater bearings, so they're 22mm by 8mm by 7mm thick, and they go on either side like that. And then we're ready to put that into the cradle. To make the cradle to hold this, there's a cradle base and there are 2 uprights, a bit of acrylic glue, and stick those in there, and then we'll be able to stick them together and that'll make the cradle. And then our rotor just clips into the cradle. Now I put a couple of extra washers there to space it out a little bit because it was catching, but we're going to turn a fan on it to see how quickly it will turn in that fan speed. And to measure the RPM, I've put a strip of reflective material there. It's just a reflective aluminium strip because we're going to use this, which is a digital tachometer, and it works by bouncing the light off that strip, so it'll count 1 rotation. So we're ready to go. Now the only other thing we've got to do obviously is exactly the same thing, but this time with the tubicles. Okay, so I've set up my fan, we'll turn it on and we'll see what happens. Now commonly these things don't start to spin all by themselves. You have to give it a little flick. It's one of the drawbacks of this style. Let's give it a flick. So we're getting about 100 RPM. And here's my tubicle version all put together. And we've got the same metallic strip there. We're going to clip it in the cradle and see what happens. We're getting 149 RPM, which is pretty cool, eh? So research is showing that integrating these tubicles into VAWT has 4 serious advantages. The first thing is it increases efficiency at low wind speed, which is of course one of the banes of VAWTs. The next thing is it reduces noise and vibration, and perhaps a knock-on effect of that is it increases durability, giving them a longer life and reducing maintenance costs. So the last thing is it increases energy capture in turbulent winds, and that is one of the key advantages because these kind of turbines really should be used in urban environments where the wind is always turbulent. Now I've put it this way just to test it, but it doesn't really matter if it's in that direction or if it's stood upright in that direction. It's easier for me to put it into a cradle to test it for you and to have a quick example, but there's a lot of ongoing research based on this biomimicry. So biomimicry, the art and science of emulating nature's brilliance. It's found a promising playground in the realm of wind turbines and turbine design. Now, as we navigate the challenges of sustainable energy, biomimicry is emerging as a guiding principle, allowing us to draw inspiration from the natural world to optimize the efficiency, adaptability, and environmental impact of wind turbines. Those towering sentinels of clean energy have become something of an iconic symbol of our commitment to a greener future. And as we seek to enhance their performance, biomimicry provides a pathway to unravel the secrets held within the intricacies of the natural world with its elegant and time-tested solutions. One of the fundamental areas of biomimicry in wind turbine design involves the study of the flight of birds, particularly the flight of owls. But biomimicry extends beyond more imitation, venturing into the realm of innovation by introducing dynamic elements inspired by the natural world. And Siemens dino tails, for instance, draw inspiration from the adaptability of an owl's wing. The main thrust of the work at Siemens has been the reduction of noise, because all onshore wind turbines have to operate below certain noise levels, and that means holding them back and curtailing energy production. So by putting a serrated trailing edge on the wind turbine blade, they've been able to reduce the noise dramatically. Siemens call them dino tails, and they've been around for a good 10 years, but they've now come out with version 2 where they've added comb structures to the dino tail serrations, reducing the noise even further, and they're claiming a 10% noise reduction without any loss in power. The combs produce microflows which aid in the noise reduction and are based on the broken feather edge of the owl's wing. Of course, Siemens aren't the only people working on this, with Seal Arbeg producing a fan blade based on the owl, and Biome Renewables producing their own version of a trailing edge adaptation based on owls. And of course there is a ton of research going on at the various universities all around the world. Bearing all that in mind, what I've done is I've redrawn this that we made in video 2110, but I've kept the tubercles, and what I've done is I've drawn a shortened version. I've effectively chopped off that tail bit there, and then I've drawn up and printed off these tails that are very like the Siemens tails, and we can glue those on there like that. Now the reason I've done this is in case anybody wants to reproduce these tails only and attach it to their own turbines, it's going to be a bit more easy to do if it's in two parts. So we glue that tail onto there and replace those tubercles with this new tubercles. Now we've got the owlet addition to the tails. Okay, so I've stuck them on, and to stick them on I've used this. It's butyl rubber tape. It allows me to fiddle with the angle if I want to. And I want to show you something really quite interesting. So let me turn the fan on. It's self-starting, which for this kind of turbine is actually quite a big deal. How cool is that? Okay, let's get a speed measurement out of it. (165 RPM), which is higher than it was, not significantly, not a huge amount higher, but it's higher than it was without the tails that we've just added on. But the main thing about those tails is it's made this self-starting. Now it's difficult to get a decibel reading in this environment, but it does seem quieter. I mean, the files are there in Thingiverse. Like I said, there's two parts to the files. I've added them to the old file so you can have a look at it yourself. And let's whiz it around and fiddle on with it as much as you like, really. See what you can get out of it. To my mind, it's pretty clear. But what the researchers are saying about this is awesome. And really you want to think about incorporating it into your own VAWTs to get, I would think, similar improvements. Anyway, hope you enjoyed the videos. Thank you very much for watching, and please do remember to like and subscribe.
204 RPM,